A gear pump is located at the rear of the fuel pump assembly. It is driven by the fuel pump main shaft at engine speed. Fuel from the tank enters the inlet or suction side of the gear pump and is carried around the outside of the two meshing gears to the outlet or pressure side of the gear pump. A pulsation damper is connected to the pressure side of the gear pump to smooth the pressure pulsations created in the fuel by the rotating gear teeth. From the gear pump, fuel flows to the wire mesh magnetic filter. From the filter, fuel flows to the inlet or supply passage of the automotive governor. Governor is a speed-sensitive device that automatically controls or limits the engine speed. It does this by varying the fuel delivered to the engine under changing operating conditions. The governor assembly performs three functions: pressure regulation, idle speed governing, maximum speed governing. Let's look at the makeup of the governor assembly. Weight assist spring, weight assist spring shims, weight assist plunger, governor weight carrier, governor flyweight, governor plunger, torque control spring, idle passage, main passage, supply passage, bypass passage, idle spring plunger or button, idle plunger guide, idle spring, governor spring, idle spring seat washer, idle screw retention spring, idle speed adjusting screw, governor shims. In the governor, the flyweights are driven through gears by the fuel pump main shaft. The governor plunger is held between the flyweight feet and rotates with the flyweights. Any rotation creates a tendency for the flyweights to move away from their axis of rotation, which is the center line of the weight carrier shaft. This outward push is known as centrifugal force. The rotating flyweights pivot on the flyweight pins. Through this pivoting action, an axial force is exerted on the governor plunger through the flyweight feet. At any given speed, the position of the governor plunger is determined by the balance between the flyweight force exerted on one end of the governor plunger and the spring force applied to the opposite end of the plunger. The position of the governor plunger is determined by the balance between the flyweight force exerted on one end of the governor plunger and the spring force applied to the opposite end of the plunger. Torque is dependent upon the quantity of fuel that is metered and injected per cycle. In the PT fuel system, at any given speed, torque is dependent on rail pressure. The control of rail pressure in the PT fuel system begins by regulating the fuel pressure supplied to the governor assembly, appropriately called supply pressure. The control of this supply pressure is accomplished through the use of a bypass type pressure regulator. This type of pressure regulator is designed to unseat when a designated supply pressure is reached. For this type of regulator to function, an excess supply of fuel must be delivered to the governor assembly. This ensures that during fuel pump operation, some fuel is always being bypassed, enabling the regulator to maintain control of the supply pressure. When the fuel pressure exerted on the button exceeds the force holding the button and plunger together, the button is unseated and fuel is bypassed to the suction side of the gear pump. The pressure at which the button separates from the governor plunger is determined by dividing the spring force acting on the button by the recessed area of the button. The recessed area or counter bore is the specific area the fuel is pushing against. For a given spring force acting on the button, increasing the recessed area reduces the pressure at which the fuel begins bypassing, thereby lowering the supply pressure. Decreasing the recessed area will have the opposite effect, that is, fuel will begin bypassing at a higher pressure, raising the supply pressure. Changing the recessed area of the button will change the height of the supply pressure curve. A button of a smaller recessed area will raise the supply pressure curve, while a button with a larger recessed area will lower the supply pressure curve. Also, with a given recessed area, any change in plunger position will change the force on the button and change the supply pressure. Increasing speed changes the plunger's position, increasing the force on the button, which raises the supply pressure. It is important to understand that there is a unique supply pressure for each speed. Supply pressure is independent of the flow out of the pump. The regulation of the supply pressure is the first step in controlling the rail pressure. The automotive governor controls idle governed speed and maximum speed by positioning the governor plunger cutoff shoulder over the appropriate fuel passage. Around idle speed, flyweight force is opposed by the idle spring. At speeds close to but below torque peak speed, the flyweight force is opposed by the governor spring. During engine operation between torque peak speed and rated speed, the flyweight force is balanced by the combined spring force of the governor spring and the torque spring. Once the torque spring is engaged, it opposes the flyweight force exerted on the governor plunger. This results in a reduction of the flyweight force, which affects the governor plunger position. The automotive governor controls idle governed speed and maximum speed by positioning the governor plunger cut-off shoulder over the appropriate fuel passage. In governing maximum engine speed, the forces acting to position the governor plunger include the flyweight force working against a combination of the torque spring and the governor spring. The flyweight force acts to close the main fuel passage, while the spring force acts to keep the main fuel passage open. Several items should be noted at this time. The weight assist spring no longer affects the governor plunger position. The idle passage has been closed by the governor plunger. The idle spring no longer affects the governor plunger position as the button has bottomed in the idle plunger guide. When the engine exceeds its rated speed, the governor reduces the fuel supplied to the injectors. The speed at which the governor begins to decrease fuel pressure is called governor brake. Governor brake occurs when the governor plunger cut-off shoulder begins to restrict the main passage. Two other terms often involved in a discussion of maximum engine speed include high idle and governor cut-off. The maximum no-load engine speed is known as high idle. Anytime engine speed exceeds high idle, the main fuel passage is closed by the governor plunger. Governor cut-off occurs at the point at which the main passage is completely closed. The difference in engine speed between rated speed and high idle speed is known as governor droop. It is usually expressed as a percentage of rated speed. Up to this point, we have established some limits for the engine operating range. A supply pressure which is controlled by the pressure regulator incorporated within the governor assembly. A rail pressure which at any given engine speed is the supply pressure minus the total pressure drop across the remaining fuel pump components. Maximum speed which is limited by controlling the engine power output. This is done by the governor which controls the rail pressure to the injectors. Within these established limits, the power output can be controlled by the operator through the throttle. The throttle shaft is located between the governor and the fuel pump discharge. It allows the operator to reduce the rail pressure and therefore the power to the level needed. The total travel of the throttle shaft is limited by two stop screws located in the throttle shaft housing. Located within the throttle shaft is the fuel adjusting screw, which determines the maximum flow area of the throttle shaft passage when it is wide open. It is used to adjust the rail pressure during calibration. While the throttle shaft is in the closed position, there is always a small amount of fuel flowing through the throttle shaft. This is defined as throttle leakage and is required to keep the fuel lines filled with fuel to cool and lubricate the injectors when the throttle is closed. Throttle leakage is an important setting on the fuel pump. If set too high, it can result in slow deceleration and excessive carboning of the injectors. If set too low, it causes a hesitation in engine response when the throttle is reopened after a downhill run and leads to injector plunger damage. In the lower speed range, the small amount of fuel flowing to the injectors is insufficient to maintain engine idle speed. the necessary additional fuel flows from the governor through the idle passage around the throttle shaft. The amount of fuel needed for idling is a total of the fuel flowing through the idle passage plus some throttle leakage flowing through the throttle shaft. With a given throttle leakage setting, closed throttle idle speed is maintained by controlling rail pressure. This pressure is determined by the position of the governor plunger cut-off shoulder over the idle passage. The closed throttle fuel pressure curve is very similar to the open throttle fuel pressure curve. The no-load idle speed on the closed throttle fuel pressure curve corresponds to the high idle or maximum no-load speed on the open throttle fuel pressure curve. Decreasing engine speed will increase the rail pressure. This increase in rail pressure along with the increase in metering time maintains a satisfactory idle speed. The change in speed between the no-load idle speed and the speed at which the maximum closed throttle fuel pressure occurs is referred to as the idle droop curve. From the throttle shaft, fuel flows to the AFC or Air Fuel Control section of the pump. The AFC assembly is needed on turbocharged engines to provide the proper fuel pressure to the engine during acceleration. It does this by controlling the fuel to the injectors to an amount compatible with the air supplied by the turbocharger. This effectively controls acceleration black smoke. The main components of the AFC assembly include cover, piston assembly, which includes diaphragm, piston, plunger, spring, retainer, barrel, spring. Let's review some basic terminology which will be used in our explanation of the AFC operation. Air pressure from intake manifold, AFC drain or vent, fuel to injectors, no air adjusting screw, fuel from throttle shaft, internal drain, plunger, spring, air diaphragm, check valve, air pressure is applied to the diaphragm and piston through the inlet fitting of the cover. Increasing air pressure overcomes the AFC spring force, causing the plunger to move in the barrel. As the plunger moves, the passage is uncovered and fuel flows through the AFC. As the air pressure continues to increase, the plunger is pushed in even further, uncovering more area until the fuel restriction is eliminated. When there is little or no air pressure applied to the AFC diaphragm, maximum fuel pressure and flow is controlled by the no air adjusting screw. Under these conditions, all the fuel flow is around the no air adjusting screw. New PT fuel pumps are currently fitted with dual spring AFC assembly. Dual spring AFC is a class fit assembly. A class fit assembly has a tightly controlled clearance between barrel and plunger, ranging from 100 to 160 millionths of an inch. dual spring AFC incorporates two hex screws on the AFC cover. The no air setting is made with the lower internal hex screw. This screw also acts as a positive stop. The AFC plunger setting is made with the top internal hex screw. Advantages of dual spring AFC are: easier to calibrate, cannot be easily tampered with, settings not sensitive to injector drain line restriction, more repeatable AFC setting, no boost pressure on AFC. Dual spring AFC assemblies are available in two standard types: standard assembly and shaped port assembly. The standard AFC contains cross drilling in the barrel connecting the AFC inlet and outlet ports. Let's take a look at the working of the standard dual spring AFC. In the no air condition, the AFC in passage is blocked by the AFC plunger. All the fuel will flow through the cross drilling in the barrel. When air pressure is applied, the plunger is pushed forward in the barrel, opening the AFC in passage and allowing fuel to flow through the AFC. On increase of air pressure, the plunger moves even further, eliminating the fuel restriction. The shaped port AFC assembly contains a shaped passage instead of the cross drilling in the barrel. The shape of the AFC in port ensures that there is always some fuel flowing through the AFC. Advantages of shaped port dual spring AFC are: better torque control below torque speed, insensitivity to viscosity during cold engine start, idle and response, better transition curve. The AFC assembly or no air adjusting screw, fuel flows to the shutdown valve. Most shutdown valves are controlled by an electrically operated solenoid. In the shutdown mode, a spring washer seats a disc, preventing fuel flow out of the pump. When the solenoid is energized, the electromagnetic force that is created overcomes the force of the spring washer, unseating the disc and permitting fuel to flow from the pump to the injectors. The main components of the PTD top-stop injector include cup retainer, filter screen, adjustable orifice, adapter, O-rings, injector cup, injector return spring, injector plunger, washer, top-stop adjusting screw, top-stop lock nut, injector link, check ball, fuel inlet, barrel, plunger metering edge, Metering orifice. Drain port. Fuel return. The injector plunger is actuated by rotation of the camshaft injector lobe. When the cam follower roller is on the inner base circle, the injector return spring has lifted the injector plunger, uncovering the metering orifice. The period of time the metering orifice is uncovered is referred to as metering time. When the cam follower roller is on the outer base circle, the downward movement of the injector plunger has overcome the injector return spring, closed the metering orifice and injected the metered fuel into the combustion chamber. The injector plunger is now seated in the injector cup. Fuel entering the injector flows through a wire mesh filter screen and an adjustable orifice located beneath the filter screen. The size of the adjustable orifice determines the flow rate through the injector and therefore the pressure at the metering orifice. From the adjustable orifice, fuel flows down an internally drilled passage, unseating a check ball. The purpose of the check ball is to prevent the reversal of fuel flow as the plunger moves downward across the metering orifice during deceleration and shutdown. The time during which the metering edge uncovers the metering orifice is the time available for fuel to flow into the cup. This begins as the cam follower roller travels down the retraction ramp toward the inner base circle of the camshaft injector lobe. As this occurs, the injector return spring lifts the injector plunger, uncovering the metering orifice. During this time, flow through the drain port is blocked by the injector plunger. Metering of fuel occurs during the entire time the cam roller is on the inner base circle. With continued camshaft rotation, the cam roller travels up the injector ramp and the upward movement of the push rod pushes the injector plunger downward. As the injector plunger moves downward, it closes off the metering orifice, completing the metering cycle. Shortly after the metering orifice is closed, the drain port is uncovered. The point at which the plunger makes contact with the fuel is determined by the volume of fuel in the cup. With an increased fuel level, the injector plunger contacts the fuel earlier, thus advancing the beginning of injection. Fuel will be injected when the pressure exerted on the fuel by the downward movement of the injector plunger exceeds combustion chamber pressures. Injection ends when the plunger bottoms in the cup. Shortly before reaching the outer base circle of the injector lobe, the roller travels over the cam nose, which effects a positive ending of injection. With injection completed and the injector plunger bottomed in the cup, the cam roller is now on the outer base circle of the camshaft injector lobe. While this is happening, the drain groove on the injector plunger has aligned the drain passages in the injector barrel, permitting fuel to flow out of the drain groove and return to the tank.